Hello ladies and gentlemen, this video is going to complete our instruction on rational functions and rational expressions. We have in the past talked about the different operations including complex fractions in our last lesson, and today what we will focus on is solving fractional equations. It'll incorporate some concepts that we have learned in previous lessons including rational function algebra, as well as solving fractional equations that we have done in the past. Now the first group of problems that we're going to focus on should look familiar. Right, they will be a single fraction equal to a single fraction, which we have done in the past, and we know that that is cross multiplication. So when we look at our first problem here, we see that we have 4x plus 5 over 2 equal to x minus 1 over 5. Now when you set this up correctly, keep in mind, and you don't necessarily have to write this particular part out, we do have a binomial in play on both sides. When you multiply a monomial through a binomial, keep in mind that distributive property will always be in effect. So when we distribute, we get 20x plus 25 equals 2x minus 2. Now keep in mind when you cross multiply, it doesn't matter which cross you do first as long as they are both done correctly. Now in this particular problem we see here we have x's on both sides. There is no exponent, which is nice, so we just use our normal solving rules. We subtract 2x from both sides. We get 18x plus 25 equals negative 2. And there's our two-step linear equation. So we subtract 25 from both sides. We get 18x equals negative 27. Now when we divide by 18 here, it is not going to divide cleanly. So just keep in mind that we do have to simplify that value, and we get x equals negative 3 over 2. Right, we have a single fraction here. Both numerator and denominator divide by 9, and there is our answer. What you could see, and this is what's going to be seen in part B, is that sometimes when we cross multiply, both parts of the cross, so x plus 1 times x minus 6, gives us a binomial times a binomial, which we will have to FOIL those together, so our result will be a quadratic equation that does need to be solved. On the other end, we have a monomial 2 times 2 minus x, normal distribution. So as far as simplifying during the cross multiplication part, we do have a little extra work here. So we do our first outers, inners, lasts. We get x squared minus 6x plus 1x minus 6. And on the other side, just 4 minus 2x. So when we combine terms on the left side, we get x squared minus 5x minus 6 equals 4 minus 2x. At this point, we now have to shift our focus to our quadratic solving steps. That 4 minus 2x has got to be shifted over so we can have the equal 0. Whether we're going to factor or use the quadratic formula or complete the square, doesn't matter. All right, so first we add 2x, so x squared minus 3x, and then we subtract the 4 to give us the quadratic in standard form, x squared minus 3x minus 10 equals 0. Now nothing in the directions indicate that we would have to round our answer or do simplest radical form, so we can go under the assumption that this should factor. There is no GCF. Normal trinomial, x times x to start our binomials, and then we look for factors of negative 10 that add up to negative 3, x minus 5, x plus 2. And then now we can incorporate the zero product law, x minus 5 equals 0 and x plus 2 equals 0, which gives us our solutions 5 and negative 2. So two possible solutions. Okay. If you need an extra minute to catch up on notes, please pause the video now. Okay. The next type of equations that we're going to focus on gives us fractions that are more than 2, where cross multiplication is not a possibility. So what we're going to do is incorporate a concept similar to what we did with complex fractions. We are going to focus on the least common denominator for all three. So we have denominators of 2, 4x, and 4x. So combined, our LCD for all three fractions, regardless of side of the equal sign, is 4x. So now what we're going to do is, just like with complex fractions, we want to clear out those denominators so we can solve whatever resulting equation we get. So what we're going to do is, using the idea of the common denominator, I want to create three fractions all over 4x, which is nice because the second and third are already over 4x. So the only fraction that really has to change here is our first one. You're missing a factor of 2x. So when I multiply that in, my resulting fraction is 2x over 4x. Now, just like with complex fractions, but for a different reason, the reason for getting the common denominator is if I were to multiply both sides of the equation by 4x, I will clear out all the denominators. And all I have to do is solve the resulting equation of the numerators. 2x minus 9 equals 3. So I get a single linear equation. There is no fractions remaining. And then I just go through my solving steps. So here we just have to add 9. I get 2x equals 12. And then just divide by 2. And when I divide by 2, I find my solution here is x equals 6. Now, as we proceed through these problems throughout the worksheet, we're going to see that the difficulty level does increase. We will see some quadratic equations that do need to be solved. But just like with complex fractions, your first focus is not on the equation you're going to solve, but getting the common denominators to be the same. If you need more time catching up on your notes on this problem, please pause the video now. Okay, as we move on to our next problem here, it is multiple choice in nature, but that does not really change how we're going to approach our problems. We have a 3-fraction equation with 3 numeric denominators of 6, 10, and 15. So what our ultimate goal is to start is to figure out what our common denominator is of 6, 10, and 15. So the least common multiple of those 3 happens to be 30. Now, what that means in this particular problem is that all 3 fractions are going to have to be multiplied by the missing factor in the denominator, and what we have to be careful is that the first 2 fractions have binomial numerators, which means, for example, in the first one, when we multiply in that missing factor of 5, we are going to have to distribute that. Right? It's not just 5 times x, it's 5 times x minus 4. So your new numerator there happens to be 5x minus 20. Likewise, in our middle fraction here, we're missing a factor of 3. So when you multiply that in, again, you must distribute, and we get 3x minus 6. So remember, when you have a monomial multiplied through a binomial, it's not just the 3 times the x or the 5 times the x, it's times the entire factor. Now, the third one's a little bit more straightforward. We're just missing a factor of 2. Monomial times monomial, you can just multiply, and we get 62 over 30. So again, same idea as complex fractions, but again for a different reason. We can now take our 30s, our denominators, and cancel them out, and focus on the equation that results across the numerators. 5x minus 20 plus the second numerator, 3x minus 6, equals our third numerator, 62. Now, one thing you are going to want to be careful about in this type of equation, if this was subtraction between the two, we'd have to be very careful about not misplacing any signs as we combine our numerators. Now, still we don't have a quadratic, however, we have some like terms to combine, and we get 8x minus 26 equals 62. Normal linear two-step equation, so we can add the 26 over, and we end up with 8x equals 88. We then divide by 8, and our final solution, x equals 11, which happens to be choice 4 from the multiple choice selection. If you need more time to catch up on notes, please pause the video now. As we go on to the next group of problems, 2 things change. One, we start looking at equations that contain more than 2 or 3 fractions. Just like with complex fractions from our last lesson, that does not change the process. It just means that we see more fractions that need to be changed accordingly, as well as a combination of numbers with variables in our denominators. So again, our first goal is to identify the LCD, in this particular case, of the 4 fractions that we have. And we have 10x, 5x, and x squared. So when I combine those carefully, I get an LCD of 10x squared. Now, we don't have any binomials to worry about in the numerator, so we're not going to have to worry about any distribution. Right? There's a lot of 1's up there, which is going to make multiplication pretty easy. But we are going to have to be very careful about making sure we find the correct set of missing factors. The first fraction just has the 10, so we're missing a factor of x squared. So x squared over 10x squared. The second fraction is missing a 10 and the x. 10x times 1 is 10x. Second fraction is missing a 2 and an x, a little bit different there. And we multiply that through, we get 2x over 10x squared. And our last fraction here in the equation is missing just the 10, so when I multiply that through the numerator, 2 times 10 is 20. So a little bit more work. We had to change 4 fractions to be over our common denominator. So if I were to clear out our denominators by multiplying them all by 10x squared, they all disappear. Now as I solve across the numerators, I get x squared minus 10x on the left equals 2x minus 20 on the right. And again, our resulting equation is a quadratic. Right? And anytime you have a quadratic equation to solve, you must follow your setup for quadratics, which means equals 0 to start. So we're going to subtract the 2x from both sides, we get minus 12x, and then you're going to add 20 to both sides to get the equation x squared minus 12x plus 20 equals 0. Now, as we look at the directions, again, nothing there indicates that we're not going to be able to factor this one. Nothing about simplest radical form, nothing about rounding, so I can go under the assumption that this probably does factor. So we can look through. There is no GCF to worry about. Nice thing is it's a normal trinomial, so we look for factors of positive 20 that add up to negative 12, which are minus 10 and minus 2. So I can go right into my zero product law, have two different factors, which implies I'm going to have two different possible solutions. And I end up with the results x equals 10 and x equals 2. Okay. So we're going to see now a few more as we move on in a second here to more problems. A lot of these fractional equations that we're going to solve can result in a quadratic equation to solve. Majority of the time, however, you can assume that they are going to factor, again, especially if nothing in the directions indicate otherwise, which will result in two possible solutions. Now, as we shift on to part B in this section, again, same idea as our last problem, only difference is now we have 5 fractions to look at. And just like we saw with complex fractions in our last lesson, nothing changes about the process, we just have another fraction tacked on that we have to identify the LCD for. So we have 2x, x squared, 4x, and 2x squared, and when I combine them carefully, altogether I do get an LCD of 4x squared. And if I look at all 5 fractions, none of them are totally there as far as an LCD goes, so I am going to have to change all 5. Some of them a little bit more carefully than others. In our first fraction, we're missing a 2 and both x's, so 2x squared gets multiplied in. Multiply that by 1, and we get 2x squared over 4x squared. Second fraction has one of the x's, but is missing the 4 and one of the x's, so we get 12x for our product here, 3 times 4x. Our last fraction is just missing the 4. Nice and easy. 1 times 4 is 4. As we shift on to our fourth fraction on the other side of the equal sign, we're just missing one of the x's. 1 times x is x. And our last fraction is just missing a 2. 1 times 2 is 2. So it took a lot of work, but we finally got our product here in all 5 cases. So if we multiply through, we can clear out our denominators. We get 2x squared plus 12x minus 4 on the left side equals x plus 2 on the right. So again, our result is a quadratic equation, which we do need to set equal to 0. So when I subtract x, I get 11x, and unfortunately that means I lose my GCF. And when I subtract 2, I get negative 6. So again, we have our, look for our GCF. Again, with 11 there, we do lose the 2 as our GCF. So if we're going to use that method here, we multiply to negative 12. 2x and 2x to start our binomials, and then factors of negative 12 to add up to positive 11 are plus 12 and minus 1. We divide out the extra factor of 2. Our actual factors here are x plus 6, 2x minus 1, don't forget, cross that out. And now we can apply our zero product law to get our 2 factors equal to 0, with resulting solutions being negative 6 for one of them and positive 1/2 on the second case. So a little bit more work. Again, we had to take 5 fractions now to get a common denominator with, and we resulted in a quadratic equation with the leading coefficient. Be very careful. Technically, we did use the guess and check approach to result in our 2 solutions. Okay, please pause the video now if you need time to catch up on your notes. Okay, now one thing we do have to watch out for is, just like many other equations that we solve over the course of the year, there is the possibility of extraneous roots, but the reason for it in this case may not necessarily be the same as the other equations that we've looked at. Since we are dealing with fractions here, the one thing we do have to watch out for is that we cannot divide by 0. So when we are done with our problem, we must make sure that all of our denominators, when we plug in our x values, do not result in 0. Otherwise, that value does represent an extraneous root. Now, just like we saw with square root equations and absolute value equations, sometimes they happen, sometimes they don't, but you must always check. So we see here again a 3-fraction equation, but we're going to start amping up the difficulty level. We start looking at some binomials and trinomials that we need to be aware of. So in some cases, to identify your LCD, you might need to factor to see what factors exist. And we see here in our second denominator the factors x plus 5 and x plus 3, which is nice because that's what we see in the other two denominators. So when we set up our 3 fractions to identify our LCD, it's a combination of the two binomial factors that we see there. And just like with complex fractions, when you are setting up your LCD, it doesn't matter if you leave it in factored form or if you want to multiply it through to the resulting trinomial, because in the end, you're going to cancel them out anyway, so it doesn't matter really how you go about checking them out. So the nice thing is our middle fraction already had both of those factors, so I can leave that middle fraction as a numerator of 18. Unfortunately, when I look at my first fraction, I have the x plus 5 there. I'm multiplying in the factor x plus 3. What makes this a little tricky is there was already a binomial there. So to get the resulting numerator there, I must FOIL. And I get x squared plus 3x plus 1x plus 3 as I FOIL out and get my first numerator. I can go ahead and combine terms now, or I can just do it in conjunction when I cancel out the denominators. That choice is up to you. If this was subtraction, I would advise you to combine terms first. So if I want to combine those, I do end up with the numerator x squared plus 4x plus 3 as my numerator, plus 18 over my LCD. Now, at least a little bit easier here in our third fraction. All I have to do is distribute through our missing factor, x plus 5, right? Monomial. New factor is a binomial, and I get 9x plus 45. So again, a lot more work now. We had binomials as our LCD, and again, the reason we don't care how we express it in this particular type of problem, as I multiply through and clear them out, they disappear anyway. So when I carry down my numerators, I'm going to have a quadratic. That's the result of the foiling I had to do in my numerators. I get x squared plus 4x plus 3, plus my second numerator, 18, equals 9x plus 45. So again, before I focus on trying to get into standard form here to solve my quadratic, I do have to combine terms there, and I get x squared plus 4x plus 21 equals 9x plus 45. Okay? So again, after a lot more work than we saw in the last couple of problems, I see a quadratic equation, so I'm going to have to subtract 9x, which is negative 5x for my b term, and then subtract 45, which gives me negative 24. So now my quadratic is finally, after all of this work, ready to solve. And again, nothing in the directions indicate that I'm not going to be able to factor this one. So, normal trinomial. And I look for factors of negative 24 that add up to negative 5, which are minus 8 and plus 3. So when I use the zero product law, I set each of these factors equal to 0, and I get a result that is x equal to 8 and x equal to negative 3. So these are my two possible solutions. And again, I use the word possible because remember now that we had in our extra step, we still have to check for extraneous roots. So in other words, what I have to make sure of is that neither of these values make any of the original denominators equal to 0. So we plug in 8. Now the nice thing is, since the second denominator is just a combination of these two factors, I really can just check x plus 5 and x plus 3, because if it makes either of these 0, it's going to make this 0 as well. So when I plug in 8, 8 plus 5 is 13. That's positive, not or negative. Here I get 8 plus 3, which is 11. 8's good to go. But here's where I have to be careful. When I look at the negative 3 and I plug it into this last fraction, negative 3 plus 3 is equal to 0. And remember, anytime you have a rational expression with 0 in the denominator, your value becomes undefined. Because of that reasoning, we must reject x equals to negative 3. So as far as extraneous roots go, that is the reasoning that you're looking for. Now what's nice about this type of equation in terms of the check goes, it's actually the only type of equation you can do the check before you even solve. All you have to do is look at each denominator and figure out what values would make them equal to 0, and if you get those results, then right off the bat you can reject them. For example here, if this is negative 5 for x, I get negative 5 plus 5 equal to 0, so negative 5 would have to have been rejected. And I just showed that negative 3 doesn't work. But again, I could have said that from the get-go as well. So we'll use that approach in our next problem by trying to identify what values or value would have to be rejected if it does pop up. If you need a minute to catch up on your notes, please pause the video now. Okay, and as we move on, again, what you're going to want to do is factor your trinomial here to make sure that the resulting binomials do match up with what you already have. All right, so x plus 6 and x minus 2 are your two binomials, which are great because that's what we see here. So let's focus on our two binomials. The first one, x plus 6 equals 0. If I get negative 6 as a solution, based on that denominator right there, that value has to be rejected. Likewise, I see x minus 2. And if x minus 2 equals 0, the result would be positive 2. So what I've shown here is that if I get either of these two values here, they'll have to be rejected. And based on the denominators that I see, all of the numbers are actually going to be fine. So the nice thing is we can do our check from the get-go. Now that we have that done, we can just focus on the solving part, which is just like we've been working on. We have three fractions here. And what we're going to focus on is identifying the LCD for all three of them, which is just a combination of our two factors, x plus 6 and x minus 2. And as we've been working on here, as we showed in the last problem, you can keep it in factored form, you can write it in multiplied form. In the end, it doesn't matter because you will be clearing them out through multiplication in the next step. So we have denominator here, common denominator of x plus 6 and x minus 2, which is nice because our first fraction is already over those two factors. It's ready to go. Now, unfortunately, just like our last problem, we see here that our numerator is a binomial, and it is missing a factor that is a binomial, which is x minus 2. So just like in our last problem, to get our common fraction here over our common denominator, we are going to have to FOIL for our numerator. And we get x squared minus 2x minus 1x plus 2. And again, when you combine your terms there, your numerator actually becomes x squared minus 3x plus 2. So this is your numerator for your middle fraction. And your last fraction here that we have to change is missing a factor of x plus 6. Now the nice thing is the numerator is just 1. So through our identity property, the numerator will just become x plus 6. So again, a lot of work. We had a factor to see what our LCD was going to be. And then when we clear out those denominators, we just focus on the combination of our numerators. First numerator plus our second numerator here equals our third numerator. Now again, it is going to be a quadratic. We are going to have to combine terms first, which give me x squared minus 3x plus 6 equals x plus 6. So it is a quadratic. Again, same set of directions, so nothing indicates that I'm not going to be able to factor. Now, in this particular case, I have to be careful because as I'm moving values over to set equal to 0, and I subtract 6 from both sides, it does cancel it out on both sides, and I get a result of a quadratic with no c value. And if you remember some of our discussions from this year, anytime you have a quadratic with no c value, you will always have a GCF of at least x in terms of your factoring. So our factors here are x times x minus 4, which still gives me two solutions. Remember, when you have a GCF that is a variable, that does result in a solution of 0, which is a value, and x minus 4 equals 0, which tells me x equals 4. Now, as we go back to the top and look at the values that we can't have, we don't see either negative 6 or 2, which means both of these solutions are good to go. Now, you might be saying, well, we just said we can't have 0 in the denominator. Well, remember, there is a difference between having 0 in the denominator and having x as 0. Because if I plug in 0 for x, the surrounding operations turn it away from being 0. Right? 0 plus 6 is 6, 0 minus 2 is negative 2. So you can have 0 as a solution, you just can't have 0 in the denominator. All right, if you need a second to catch up on notes, please pause the video now. And that finishes up our discussion with fractional equations. Over the course of the last few lessons, we've learned many of the operations that need to take place with fractions, right? By factoring to cancel out and simplify fractions, factoring to cancel out factors to multiply fractions, same with state change, flip, and division. We've also found common denominators to do addition and complex fraction work, as well as finding the common denominator here to solve fractional equations. Thank you for watching.